Hey guys, and welcome back to my channel. In today's video, we are going to look at some of the advanced concepts used in developing a RAG-based application. In one of my previous videos, I have already explained about RAG, what it is, how it is used, and how it empowers the LLMs that we use in daily life in order to create a knowledge assistant. In this video, we are going to look at some of the advanced concepts. But let's first revisit what happens in RAG. There are two steps in RAG. One is indexing, other one is full RAG cycle from retrieval to the response. Let's see what happens in indexing. We have a data. We process all these data into some kind of documents, and then these documents are divided into different form of chunks. These chunks are passed in the embedding models. The embedding models create embedding vectors, and then these vectors are stored in a special databases called as vector databases. Now, what is a full RAG cycle? We have a query. The embedding model takes the query, it creates an embedding vectors, and then this embedding vectors uses a similarity search with our vector databases and then retrieve the document. This retrieval is done by a retriever, and once the documents are retrieved, it is passed as a context, and this context along with the question, which is our initial query, is passed in our LLM as a prompt. Using this prompt, the LLM will generate the response. So this is how the complete RAG cycle looks like. Now there are three places where we can actually improve the RAG applications. There can be failure point in indexing the data, retrieval, post-retrieval, all these things happen. So if we look at the RAG properly, we can see there are 3 points where we can improve the RAG. So first one is in the indexing itself. When the document comes in, and it is stored in different kind of chunks, and then finally is being stored in the vector databases. This is one of the places where we can actually improve. So this part is called as indexing optimization. The second one where we are going to find some kind of improvement is the place when the query comes in. So the second improvement scope is query, and we say it as query optimization. Finally, once all the documents are retrieved and it is passed into the LLM, that is also where we are having the scope of improvement. This scope of improvement is called as post-retrieval. So there are three stages where we can actually improve. Once when we store the data. Second, when the user inputs a garbage, we can actually improve the query. And the third point is when whatever the context is being coming in into the LLM, we can actually improve the context itself. These are the three areas which we are going to look into, and this forms our advanced RAG. So in indexing improvement, we have a chunking strategy. There are different kind of chunking strategies. Basically, chunking means dividing the data into small parts and then using those parts for the retrieval. But why chunking is being described over here? Because if we have the small size of documents, there is no kind of information overload. We have a fast and accurate response. And how do we do it? Chunking can be done on the type of context, type of embedding model, user queries, and the purpose of the application. So let's say type of context. We have a different kind of documents, news article, documentation, code blocks. We cannot use the same kind of chunking strategy for all kind of different documentations or the different kind of articles. That's why chunking will differ based on the docs that are coming in. For the embedding model also, if we use the mini LML6, the output token, that is the embedding size of the vector, is 376. Meanwhile, a BERT will give a 512. So we have to limit the chunking based on the size also. We have user queries. Let's say queries are detailed, it is generic, it is crisp and concise. So all these factors basically helps us in deciding what kind of chunking strategy we are going to use. First one that we are having over here is a fixed size with overlapping sliding window. This method basically chops the text into equal size chunks based on the character count. Overlapping chunks ensure that sentences or the concepts aren't abruptly cut in half. It is simple to implement but ignores semantic context. So this is what the fixed size chunking is. We have a small blocks, but we have a sliding window that basically overlaps so that we don't have any abrupt cuttings over here and we maintain the coherence. But it doesn't have any kind of dependency information between these. Next one that we will look at is the recursive structure-aware splitting. This hybrid method attempts to balance chunk size with natural language boundaries. It recursively splits text based on the hierarchy of separators, ensuring each chunk remains coherent unit. So we can basically divide on double spacings or a single spacing and so on. So recursively, it will go on splitting the text based on these kind of separators. And then there is a structure aware splitting that basically splits based on the sentences, based on the paragraph. So splitters can be dot, comma, semicolon, and all these things. And then there are other form of chunking. First one in this is content aware splitting. Content aware splitting basically tells to split the document based on the content. Let's say we have a markdown file. It can have a headings, different kind of heading levels, and then we can chunk based on these heading levels. We have a Python code, we have a JavaScript code, so we can basically separate the text and then we can separate the code and then we can do the chunkings. There are other format of the chunking also, that is basically semantic chunking, LLM based or agentic based chunking. All these things we are not going to cover in our this video. Next method to improve the indexing is the parent document retrieval. So basically we store the data in such a way that we do have small chunks, but these chunks will be linking to a parent document. This will be a big document. So when we have a retrieval based on these chunks, we are not going to retrieve the chunks directly, but we are going to put the parent document directly into the LLM. So this way, we are not losing the context or we are not missing the information, and then we are providing a better coherent response. Okay, so that was all about indexing optimization. Now let's see how we can optimize the query. First one in this is multi-query. So what happens in this, we basically generate the reformulation of the user query in multiple query. So let's say user enters a query, and then we will generate four different formats of this. In all these different formats, we are basically having certain kind of variation, but a very subtle variation, not a very different variations. Let's say we can have a synonym different. Let's say we have another look onto this. Let's say a very generic question is asked, but we can go into the detailed prompt. So these kind of different queries are generated, and then based on these queries, all these queries, we retrieve a document, and then finally take one document that is being passed into LL. Second thing in this is a query decomposition. So let's say a user puts multiple questions in a query. If we have a 3-4 question in a query, we might not be able to retrieve a document for all these questions. So what we do, we split this query into 5 kind of different queries. This allows us to have a multiple queries, and all these multiple queries will have a retrieved document corresponding to them, and then we can have a finally big document which will be passed into the LL. Third step in this is a step back prompting. So step back prompting is something like general reformulation of the user query. Let's say a user asks something very specific to a mathematical concept or a chemistry concept or a physics concept. But we will have a model, maybe a different kind of LLM, that is going to take a step back. So let's say we have a very specific query. It is going to generate a generic response for this. Once we have a generic question generated, we can have a document retrieved for the concept, and then we can use this concept to solve the question. A user asks, what is 2 multiplied by 2? Maybe we can basically go back and then say what multiplication essentially means. Once we know what multiplication essentially means, we can put or use the concept to derive what is 2 plus 2. So this allows us to generate a simple query or a generic query from a very specific query, and then we can generate a step-by-step answer. And then we have a semantic routing. In the semantic routing, we can basically route the questions based on semantics. There is another concept where we use a LLM kind of routing technique, where LLM will decide which kind of path does a particular query should follow. What do we mean by routing over here? We see the question is based on which topic. Let's say it is a legal question or an HR question or something related to science question. So all these query when they come in, they will be basically deviated into particular set of documents so that we only look into this kind of documents, not into the whole database, and then we save time and then we retrieve the better documentations also. And thus we improve the knowledge base that is being retrieved and then we have a better response. So the two techniques till now that we saw were basically pre-retrieval techniques. So indexing and query. Both were the steps that were happening before the responses or the before the documentation or the context were retrieved. Now we are having post retrieval. What happens in this? We basically do the re-ranking kind of thing. In this, one of the step is called as rack fusion and the other one is cross encoder re-ranking. In the rack fusion, what we have a query and then we have multiple queries corresponding to it. For all the multiple queries, we have a different kind of documentations or the documents retrieved from our vector databases. Once we have a documents retrieved, we are going to apply reciprocal rank fusion. And then this reciprocal rank fusion is going to provide a score to all these retrieved documents and then provide a separate kind of ranking to all these documents. Once we have these kind of separated rankings, we are going to take the best one and then pass it into LLM. Finally, we have the answer. What happens in the reciprocal rank fusion is it basically pays more attention to the document that is appearing high in all kind of query and the retrieval. So let's say we have a document D2 which is ranking 1 in all kind of retrieval. That means it is going to get a highest score in our this and then D2 will be coming over here and then D1 might be coming over here. Finally, the D2 will be added to the LLM. It will be used as context and then we have the answer. So it basically pays attention to which kind of document is appearing with high score in all kind of retrieval and then it will be having the maximum score. There is another way of re-ranking where we use a different kind of model called as cross-encoder model. What happens in a cross-encoder model? It is basically different from bi-encoder model. Till now, what happens in a bi-encoder model? We have a query and then we have some kind of documentations. These are put separately into our embedding model and then finally we have some kind of similarity score calculated and we get the response. Okay, but what happens in a cross-encoder model? Query along with the document that is passed into a pre-trained model. Let's say we have a word and then we get what kind of similarity is present over here. How can we do it? We have a query, we have a separator token and then we have a document. So this way we are basically passing both together into a cross-encoder model and then we have a better and deeper understanding of which documents are basically more similar. But this cannot be done at the step 1 where all the documents are retrieved because among the millions of the documents we are going to find some, let's say, thousands of the documents and then we are going to pass it into the cross-encoder model and then we are going to get some 10 documents. So this million document retrieval through the cross-encoder model can become very slow. That's why we use bi-encoder initially and then we do the re-ranking using our cross-encoder model. So that's how it all looks. That was all for the advanced RAG techniques. We may look at different concepts and more advanced concepts in upcoming future. But before that, I just want to showcase, I'm going to basically create some kind of pages like this. So in case you get confused by the video, you can go ahead and read it. Usually it will be hosted through GitHub profile, not any kind of domain, but it will be very helpful for all those who are going to read it. Thank you for staying with me. I hope you all have a good day. If you like the video, please share with your friends and like, share and subscribe.